We have the pleasure of having with us Abby, who is a PhD student from the National Tsing Hua University in Taiwan. Abby is working on the Crab pulsar, and specifically in a sort of unexplored regime in the hard X-ray MEV to gamma ray range. He is part of the COSI mission, and this is actually how we've met through the COSI mentoring program. But he's also part of the Gamma Ray Transits Monitor mission, which is the first astronomical CubeSat mission from Taiwan. And they're all focusing in the MEV range, which I've said before is sort of unexplored and will likely give us very, very exciting results. So today he'll tell us a little bit about his work on the Crab Nebula on slightly lower energies, but it should still be equally exciting. So Abhi, thank you very much, and please take it away.
Thank you for this introduction, Anis. So today, hi everyone, my name is Abhi, and I'm a third year PhD student, as Anis mentioned, in Taiwan. So the title of my talk is Anticorrelation between Photon Index and Flux in the Crab Nebula, which is revealed by multiple hard X-ray instruments. So this work has been published. There are two publications associated with this work. Both are published in APJ. So the outline of my talk is going to be background and motivation. Then I will talk about how different instruments were used. Especially, I will talk about SIFT-BAT, and then I will show the spectral analysis and the results. So then, how the physical interpretation of this anti-correlation is moving forward, and the outlook. So to begin with, what is a pulsar wind nebula? So to answer that question, we need to know how a pulsar wind nebula forms. When a massive star, like about 8 solar masses, runs out of nuclear fuel, it collapses as a supernova explosion and forms a neutron star. If it is massive than like 12 solar masses, it forms a black hole, as we know. And if it is less than that, it forms a white dwarf. So in this 8 to 12 solar mass regime, it forms a neutron star. The neutron star, if this neutron star spins and has a high magnetic field, we call it a pulsar. And these pulsars emit charged particles, particularly positrons and electrons. And these charged particles form a wind and hits the surrounding supernova remnant. So this supernova remnant, when it hits there, it forms a termination shock where particles move through synchrotron radiation and emit electromagnetic spectra across the electromagnetic spectra. This is known as pulsar wind nebulae. And now about Crab Nebula. Crab Nebula is a supernova remnant or pulsar wind nebula created by the explosion of a massive star in 1054 AD. It is located about 2 kiloparsecs away from us, and it is located in the constellation of Taurus. And this Crab Nebula is categorized as Messier 1 or M1 in Charles Messier's famous catalog. And the heart of this Crab Nebula lays the Crab pulsar. It's a neutron star with a 33 millisecond period, and it ejects particles. Since it's a relatively new supernova remnant, it ejects particles very very well, and it creates jets and filamentary structures around the pulsar. Now, let's talk about the synchrotron radiation from Crab Nebula. So, since it is very high energetic and a place, we can study about particle acceleration, magnetic fields, and shock processes in this Crab Nebula. The relativistic electrons spiral in the magnetic field and produces the synchrotron radiation, like I said before. The wind termination shock is a powerful mechanism for accelerating particles. through diffusive shock acceleration. And we will talk about that later. So Crab Nebula is one of the brightest persistent sources in the electromagnetic spectra. It follows a power law spectra in this X-ray, gamma ray regime. As you can see here, it is a simple power law spectra. And we use this Crab Nebula to calibrate multiple X-ray instruments. Next, about the motivation of the study. So in this table, you can see that the multiple X-ray instruments, their energy range, the absorption feature, and the spectral index of the spectrum. So as you can see, the spectral index is different for different energy ranges, as well as if we use different spectral models, even then it is different for different energy ranges. So even though the Crab Nebula is considered to be a standard candle, we want to see if there is any variation. And also photon index and flux relation has never been studied before. So we wanted to see that too. And also this is from another paper called another paper from SIFT-BAT experiment. And from this paper, you can see that the Crab nebulous count rate is very variable and also follows something like a sinusoidal function. And it drops very abruptly around 2010. Oh, this x-axis is the time in SIFT-BAT mission month. So this 0 is when the SIFT mission started in 2004, and here it's about 2010, and there is abrupt drop, and you can see it varies for multiple instruments, RXT, integral, Fermi, and SIFT, and the RXT, Fermi, and SIFT agree very well, and even integral agrees after some period of time, and the exact acceleration mechanism is not set on stone. We don't know. We know that it is a diffusive shock acceleration or some other mechanisms, but we are not completely sure about it. And we also wanted to know if there is a long-term trend in this change. And now about the instruments. So for our observation, we used 3 satellites and 4 instruments. From RXTE, we used PCA and XT, which is PCA is proportional counter array, XT is high energy X-ray transient explorer, and we divided the PCA into 3 to 10 keV and 10 to 50 keV band. We divided it such that 3 to 10 is soft X-ray and 10 to 50 is hard X-ray. And RXT, XT we did not divide because it's already in the hard X-ray band. And New Star, we divided it again, so it's become 3 to 78. So we divided from 3 to 10 and 10 to 78. And for SIFT-BAT, it's from 15 to 150 keV. And here are the instruments in the figures. So now let's talk about how SIFT-BAT data was taken. So SIFT-BAT is a survey telescope. It only records event mode data when a GRB is triggered, and other times it collects data in the binned mode, binning into 8 energy bands and 300 seconds. So one cannot get a good spectrum from it. So from the binned mode, so I have to use the unbinned mode, which is the when the GRB trigger is recorded. So what we did is that we took a 25-degree radius around the Crab pulsar position. This is the Crab pulsar position, the red dot, and we took a 25-degree circle around it. And we took all the GRBs that are in that region, and we took the GRBs and we started analyzing that data, GRB data. And when we made a light curve using that GRB data, we observed the 3 parts like this, three parts. And this data, this light curve is already background subtracted. And in the first part, it is the pre-slew period where the satellite is just observing the sky. It is a huge field of view. So as you can imagine, it is observing the sky for GRBs, and it suddenly observes a GRB, and we can see a trigger there. And as soon as it observes a GRB, it suddenly starts to uh, roll over or slew towards the GRB to point its narrow field instruments towards the GRB. Then this we can observe the rate increase of the crab, and also after the slew period, we will have the post-slew period where there is a constant uh, flux or rate, and we took this post-slew period for our analysis. From this 18 years of observation, we got 38 good observations. And from that observations, we made a spectrum. It's a simple powerless spectrum as we discussed before. So we used XPEC for our analysis. XPEC is the standard X-ray spectral analysis tool. And from this plot, the slope of this spectrum is the spectral photon index, which is the gamma. And we had this long-term observation. And then RXT and New Star, we used them, like we divided them into these energy ranges and took the observations. For them, it is normal observation. So there is no special thing that we did like for crab, for bat. And for results, result one, we show that the flux, this plot is for SIFT bat, and this is for all the other instruments. In SIFT bat, as you can see, when the flux is lower, the photon index is higher. This dashed line is the average, and here too. And as you can see, when it is lower than the average, here photon index is higher than the average, and similar for other points. When it is higher, it's lower, it's lower, it's higher. And so that is the anti-correlation that I was talking about in the beginning. And also we can see that there is a sine wave fitted here, and it was not a good fit, but although it was not a good fit, we obtained a 6-year period for both of them. So we think that this the variations time scale is 6 years. And these green dots represent data taken from a survey, from SIFT-BAT itself. It is performed by the SIFT-BAT officials. So they perform a 157-month survey catalog, and the crab's rate is discussed like this. And we plotted it in the crab units, and as you can see, there is a good trend, like agreement with our data. And this is for the SIFT-BAT instrument. Coming to the other instruments, we can't see very clearly because there are many data points here. But if you observe closely, the if there is also anti-correlation here too, and this can be shown here in this plot. So this is for all the other instruments. This is for SIFT-BAT. And for other instruments, let's see, this 3 to 10 keV, this is for RXTE PCA, small energy range. And you can see a negative correlation, anti-correlation here. And this is for more higher energy, hard band. There's a anti-correlation here also. And then this is for XT, and XT goes to higher energies. As we go to higher energies, the trend is more pronounced. And this is for New Star. New Star has 2 modules, FPMAA and FPMAB, FPMB. So these 2 modules for the lower energy ranges, even though the anti-correlation is not clear, for higher energy ranges, so 10 to 78 keV, the anticorrelation is pretty much clear. And for shift bat, it is definitely very strong. And in this slide, you can see the statistical uh, Spearman's rank correlation coefficient to see how good does it agree and agrees with the anti-correlation. And for shift bat, we observed a 0.69 with a p-value of 10 to the minus 6. And here for RXT PCA, you can see in soft bands even it's higher, but in harder bands, it's even higher. But for new star, there is a problem, like not a problem, it's not that strongly pronounced, but for harder bands, it's strongly visible. Now, this is the other result. It is from, as I showed you, this green points. We took these green points and we plotted it into a hardness ratio plot, and we separated them into two instances. The first 72 observations till December 2017, and I'm sorry, there is another typing mistake here. It's 2010. So the first 72 observations till 2010, and after 2010, we divided it in such a way that here there is a sharp decline. So we took the points after this sharp decline as something, and before that as something else. And we found that the points after 2010 have stronger correlation than points after points before 2010. And from this hardness ratio plot, what we can say is that when the rate increases, that means the spectrum becomes harder, the spectrum becomes brighter. That is, there is no more photons when the spectrum becomes harder. And now comes the acceleration mechanism. This harder when brighter behavior is seen in all three instruments. Also, the emission can be said that it is from nebula only, because not only but mainly nebula, because pulsar emits very low energy, very low amount of photons in this energy range. And this acceleration mechanism that is going on here is known as diffusive shock acceleration, where pulsar winds gain energy through magnetic reconduction or turbulent magnetic relaxation. These particles then go to the termination shock of the PWN and produces synchrotron radiation there in higher energies. It gains higher energy through acceleration by going back and forth the termination shock region. And then the acceleration mechanism. This is the only slide I have with the equations, so bear with me. The first equation is the synchrotron radiation spectrum of emitted particles, emitted relativistic particles. So this nu is the frequency of the particle. So this is the energy of the synchrotron radiation spectrum described by here. And P is the power law index, electron power law index. So this power law radiation electrons, power law radiation of electrons produced by power law index of spectrum. And this P and this gamma are related by this equation. This gamma is the photon power law index. This photon power law index is observed one that we showed here, this gamma, the slope of the spectrum, or here this in the equation, this gamma. So what these two are, there is a relation between them. So the theoretical electron photon index and observed photon index are connected. Now there is another equation, this equation. So this equation shows that here there are two parameters that I need to explain: the capital P and the small and this beta. Capital P is the probability that a particle remains in acceleration region after each collision in the diffusive shock region, and beta is the energy gained by the particle while going through each collision. And the observed variation is usually the variation that we talked about is if we assume it is due to magnetic field strength, then a stronger magnetic field strength makes it harder for electrons to escape the shock front, which increases the probability P. So the probability P is increased uh, that the collision takes place. When P increases, this small p decreases because of this relation. And when small p decreases from this relation, gamma also decreases. This means that higher flux means higher magnetic field, which leads to higher flux, and the higher flux will lead to smaller photon index. So this is how it is connected with each other. And now for the physical interpretation, as we talked before, the physical interpretation is that the diffusive shock acceleration supports synchrotron radiation in nature, and the variation in magnetic field strength around the shock front is also the main reason for this limited observed spectrum. And we can also say that the crab is not perfectly constant. There are dynamic calibration should be done for instruments because there might be changes during time, and also in different missions, different energy ranges, the calibration should be is completely different and should be taken with care. And there are some limitations for our study. The limitation number one is that our study is done for lower energy ranges. And at higher energy ranges, the pulsar contribution is very high, and it dominates the nebular contribution. And we can't resolve the pulsar and nebula separately. Maybe it is hard to do. Maybe we will try that in the future to do, maybe using Fermi-Lat data. And also, while magnetic reconnection one can be one reason to say that the particles are accelerated to higher energies, this this magnetic reconnection time scale is usually very low. So we need magnetic field changes in large scale as well as in large time scale for explaining this acceleration mechanism. And to conclude my talk, anticorrelation is a persistent and intrinsic property of synchrotron radiation. Also, Crab Nebula varies surprisingly high, and we should explore this in multi-wavelength analysis. Thank you for listening to the talk, and I'm open for questions.
Okay, thank you very much, Abby. That was great. Do we have any questions? Don't can open your mic or raise your hands. Or in the meantime, I can ask: do we expect to see this anticorrelation in other sources as well? If this is has been seen, or is just Crab bright enough that allows us to do stuff like that, and see this trends?
So we have not seen any other work in literature that shows this, but in black hole X-ray binaries, this has observed. But in black hole X-ray binaries, I think this has been observed, right? I think yes,
But not pulsar with nebula.
but not PWN. No.
Okay, very interesting. Do we have other questions for Abby?
Yes, I have a question, Abby. Hello. Thank you for
Yeah.
the talk. I was wondering if there was an event or something that was found for to explain that separation between the before 2010 and after 2010 data that you showed.
Yeah.
Yes.
So even here we can see that the difference that you said, but we are not sure if there is any mechanism involved. So even in the paper that we wrote, we just said we don't know what happened exactly.
Okay, thank you.
Yeah. But it has been observed by multiple instruments that there is this sudden drop and a difference. So yeah, it is real, but we don't know how to explain that.
Thank you, Abby.
Yeah, sure.
Any more questions? Going once, going twice. Okay. So thank you very much, Abby. Hopefully
Thank you
one
for
day
inviting me.
you'll manage to get to have you here in person as well.
I think next time I will have a longer talk. Yeah.